have to do with things looking at each piece as you go along. So, for example, when they say fourth partial sum, what they mean when you look at this particular summation, you'll notice that in the top part, or in other words, the number you're going to stop with, they have an infinity there. That means you keep adding forever. So a partial sum means change that number to a 4. So the fourth partial sum is talking about just go to the fourth one. So the way I would do that problem then is I would rewrite it as the sum from I equals 1 to 4 of 1 over 2 to the I power. And then our process would be the same as we've been doing in the past. So I would start out with 1 over 2 to the first power plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the fourth. And I would add all of those up. So what I would see is that I have 1/2 plus 1/4 plus 1/8 plus 1/16. And if I put those all together, I think I get 15/16. Somebody can check my math on that. And that would be the fourth partial sum, or in other words, add up the first 4 things. So this next part, the approximate final sum, is really talking about what happens as I go to infinity. So if the top is infinity, what is my sum going to be? And as you look at this, what would be really interesting is to go, okay, what happens if I just add one number? So if I looked at just the first partial sum, that means I look at just the thing that was in the light blue, and that would have been 1/2. Well, okay, what if I would have added the first 2 things? Or in other words, I got the second partial sum. That would have been the 1/2 that I had from before, plus the 1/4 that showed up in the purple. And if I got a common denominator, I would find out that those 2 things together would be 3/4. Because 1/2 is like 2/4. Add another fourth, that's 3/4. And then, if I went to the third partial sum, which was in the pink, meaning going all the way up to the pink, that is, add the light blue, the purple, and the pink, the third partial sum, we see that we had 1/2 plus 1/4 plus 1/8. And if I get a common denominator of 8ths, you find out that your answer is 7/8. So now this is interesting. 1/2 is the first partial sum. 3/4 is the second. 7/8 is the third. 15/16 is the fourth. I bet you I could predict what the fifth partial sum would be without doing any math. Drew? 31/30 seconds is correct. Notice how the bottom is doubling each time, and the numerator is always 1 less than the denominator. So if you were going to infinity, so you added forever and you never stopped, your sum would be 1. Is whenever they talk about things going to infinity, these things that go to infinity, we talked about these with graphs. These things are called the limits. So that 1 is really our limit. In number 9, we're just going to go backwards. And this is kind of like finding our a sub n term, except we're just going to write it with summation notation. And what I notice is in this first one in 9a, that from 1 to 4, I'm adding 3. From 4 to 7, I'm adding 3. So on and so forth. And every single time, I'm adding 3. So when I write my summation, the first thing that I'm going to write down is 3n. Just like I did with my a sub n term. And I usually like to start with the number 1. So I'm going to tell you that my n starts with 1. If you wanted to use an I, you would have had 3I, and I equals 1. What does the 1 down below the E mean? Joe?
That means where the n starts at.
That's where the n starts. Or in other words, plug a 1 in first. How many different things are there here? 8. That means the top number is going to be 8. Now let's just see if this works out fine. 3 times, what number do I plug in first? 1 is 3. Is that what I wanted?
No.
Oh, darn it. So I've got to
-2.
subtract off 2. And what you see here in the gray circle is the sigma notation sum of the series that was written before us. Look at the second one. In part B, what do you notice about the numerators of every single thing? Very good in listening to my question. Let's try again. What do you notice about the numerators of every single one?
0.
They're all 1s. So when I do my sigma, what I know is that I'm going to have a fraction, and the top's going to be a 1. And if I were to cover up the first fraction, actually I'm not going to cover up the first fraction. What do you notice about the bottoms? Or actually, let's even back that up. I'll even go back one more than that. Let's just say I want to use the letter I this time. What number do you want to start with? 1, okay. So then, if I want to start with 1 and there are 5 things, what should the top number be? A 5. Do you notice anything about the denominators? What you should have noticed about the denominators, because we talked about it earlier, is that every single one of them is a factorial. Or in other words, I have I factorial, and that's why I chose I. Look at that. Look at the denominator. Dot, dash, dot, dash, dot, 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 dash, dash, dot.
Morse code.
Here, let me help you.
Morse code.
Some people are struggling, so.
Morse code.
I factorial. This looks cool.
I caramba.
Dude, my IQ.
So if you'd actually like to listen and learn, in this summation, the big tricky thing that some of you may not have noticed is there's not 3 terms because there was a 3 on the top. Because we didn't start at 1. We started at 0. So the 0 term, the 1 term, the 2 term, the 3 term means there are 4 terms.
Oh, I won't.
Each consecutive parentheses is a different color. So in the red is where I'm plugging in the 0. In the light blue, I'm plugging in the 1. In the pink, I'm plugging in the 2. In the orange, I'm plugging in the 3. If you calculate each of those, you get 1, 4, 8, and 15 consecutively. And if you add those all up, your final answer is 28.
My stomach's